Hello, this is the section 12.2 lesson. For this lesson you're going to need your calculator. The calculations for this section are very complicated, so we're just going to let the calculator do all the work. To motivate this type of hypothesis test in this section, let's look at this example. Let's suppose that we're farmers and we grow cucumbers, and we've got 4 different patches of cucumbers. In one of these patches we fertilize, another patch we irrigate, on a third patch we both fertilize and irrigate, and then in a fourth patch we don't give any sort of treatment. So we've got here 4 different populations of cucumbers, and the question here is, do these 4 different populations have the same mean weight? So we want to compare the means of 4 different populations. Well, in order to answer this question with 100% certainty, I'd have to go out and pick every single cucumber from all 4 of these patches, weigh each one, add up all those weights, divide by the number of cucumbers in each patch, and compare those 4 population means. Now that's impossible. I can't do that. That's too many cucumbers to pick and to weigh. So instead, let's suppose we go out and we randomly select 5 cucumbers from each patch and we weigh each one of them. So suppose we go out, we pick a first cucumber from the patch that has no treatment, and it weighs 0.15 pounds. The next cucumber is very small, weighs only 0.02 pounds. Suppose we go to the patch that was irrigated. The first cucumber weighs 0.23 pounds, the next weighs 0.04 pounds, and so on and so forth. So each one of the numbers in this table represents the weight of a randomly selected cucumber from that particular population. And so if we just glance over the numbers real quickly, notice that these cucumbers over here from this patch tend to be kind of larger than most of these other cucumbers. These cucumbers over here tend to be kind of smaller. So it looks like maybe the answer to our question is no, but that's just a real rough guess. We want to get some more analysis done to the data to support our conclusion. Well, let's set up our formal hypothesis test and define our parameters. So first of all, we're going to state a claim in words. And this claim is that the different treatments have the same mean. So in other words, we're claiming that our 4 populations all have the same mean weight. Now, just a cursory glance at our data indicates that this claim is probably not true, but still we're going to go ahead and claim it. So we've got the next step is to define our parameters, and we have 4 parameters. Mu1 is the mean weight of all cucumbers in that first patch that was given no treatment. Mu2 is the mean weight of all cucumbers in the second patch given fertilizer, and so on and so forth. So each population has its own mean. Each population has its own parameter, mu1, mu2, mu3, and mu4. So the next step is to state our hypotheses. The claim in mathematical notation is that mu1 equals mu2 equals mu3 equals mu4. That's just a mathematical way of stating that these 4 populations all have the same mean. The alternative hypothesis is the opposite of this null hypothesis. The opposite of that they're all equal is that at least one of these means is different. Now, that could mean that all 4 of the means are different. It could mean that 3 of them are equal and 1 of them is different. It could mean that 2 of them are equal and the other 2 are different. A lot of possibilities. But in general, the alternative hypothesis is that they are that at least one of them is different. So in this type of hypothesis test, we are claiming that 2 or 3 or 4 different population means are equal. That's always going to be our null hypothesis, and the alternative is always going to be the statement that at least one of those means is different than the others. So now let's talk briefly about our analysis. Now the analysis here is actually very complicated. We're just going to try to get the basic idea of what's going on here. So we want to compare population means. So the first thing we might want to do is to construct or calculate the sample means. And so for our first sample here, from this patch that received no treatment, we can add up these 5 numbers, divide by 5, and that gives us our sample mean for that patch. We can do the same thing for each one of the other patches. So here are 4 sample means. Now this sample mean right here is an estimate of mu1. This number here is an estimate of mu2, an estimate of mu3, and an estimate of mu4. So notice that those 4 estimates are all different. The fact that those are different is referred to as variation between the samples. The fact that these are all different indicates that, well, maybe my 4 population means are not all the same, and so that would cause me to reject the null hypothesis. Well, as we've pointed out before, whenever we compare sample means, we also need to take into account the standard deviations. And so for each one of our samples here, I've calculated the standard deviation, just like we did back in Chapter 3. And so here's our 4 different standard deviations. Now notice that these 2 standard deviations here are pretty small. That means that these data are not very spread out. They're all pretty close together, which means that this number here is probably a pretty good estimate of mu1. Likewise, this number here is probably a pretty good estimate of mu3. And but now if we look at this standard deviation here, notice that it's pretty large. That indicates that maybe this number here is not a very good estimate of mu4. Likewise, this standard deviation is also fairly large, means that this number here may not be a very good estimate of mu2. And so these So the fact that we've got some maybe large standard deviations would cause us to question our conclusion that the population means are not all the same. And so there's kind of a lot going on that we need to take into account. Now these standard deviations, as we've mentioned before, are measures of how spread out the data are, or stated another way, they're measures of variation within the sample. So in this type of test, the analysis, we need to compare the variation between the sample means to the variation within each sample. So we got to take into account the sample means as well as the sample standard deviations. And this type of test is called analysis of variation, or ANOVA for short. Now there are lots of different types of ANOVA tests. The specific type of ANOVA test that we're doing here is called a one-way ANOVA. So the calculations for doing a one-way ANOVA are very, very complicated, so we're just going to let the calculator do all the work. And the way the ANOVA test on the calculator works is a little bit different than some of our other hypothesis tests. The first thing that we have to do is enter our raw data into lists. And so remember how to do that on your calculator. Go to the Stat menu and then Edit, and you're going to get a window that has your different data lists on it, L1, L2, L3, and then if you scroll to the right there'll be an L4. And so we need to enter our first list of data in L1, the second in L2, L3, and then L4. So this is the data from the patch that received no treatment. This was the fertilizer, this was the irrigation, and this was both. So we just need to enter that raw data into our calculator. The next thing we do is we go to the Stat menu and then Tests, and then choose the very last option called ANOVA. It may be option H or option G depending on what type of calculator you have, but you see it right down there, ANOVA. Now when you select that command, it's going to paste an ANOVA symbol or ANOVA command on your blank home screen. The next thing we have to do is enter the lists containing the data. So you're going to enter L1, L2, L3, L4. And remember, we access L1 by pressing second 1, and then L2 is second 2, and so on and so forth. So you're going to enter all 4 of those lists with a closed parenthesis there at the end, and you're going to hit enter, and this is the screen that your calculator should give you. Now this gives us a lot more information than what we really need, so let's just talk about a few of them. So first of all, the first row, we see that this is one-way ANOVA. That's exactly what we expect. This number right here, f equals 5.73, this is our test statistic. This type of test statistics come from a distribution called the F distribution, named after a guy named Fisher. The next value is the important one. P equals 0.0073. That's our p-value. And for our purposes, this is the most important value. There are other outputs here, factors, and if you scroll down, there's even more factors. We won't get into what those mean. If we were doing some more detailed analysis, we would look at those factors. But for our purposes, the only value we really need here is the p-value. Now, we're going to interpret this p-value in the exact same way we've interpreted every other p-value. We're going to compare that p-value to our significance level. No significance level is given, so we'll use the default 0.05. And this p-value is obviously less than 0.05. And so our technical conclusion is to reject the null hypothesis. Now we're going to come to the final conclusion, and in the exact same way as every other hypothesis test. We'll start here. The original claim does contain equality because the claim is that all 4 population means are equal. You reject the null hypothesis. Yes, we do. And so here's our final conclusion. There is sufficient evidence to warrant rejection of the claim that the different treatments have the same mean. So, in other words, it appears that the different treatments appear to produce different weights of cucumbers. So that was kind of our original conclusion just by glancing at the data, and our hypothesis test indeed supports that conclusion. Now let's talk real briefly about this word treatment. This word treatment, or also called a factor, is a very generic term, and it's a property or characteristic that allows us to distinguish the different populations from one another. In this case, a treatment has a very physical meaning. A treatment is what we did to the different patches of cucumbers. But a treatment could be just a name that we give to different populations, or maybe it's a color that distinguishes one population from another. Treatment, again, just a very generic term that allows us to distinguish one population from another. Okay. Now, real briefly, let's talk about the final project. There will be a final exam and a final project. We'll talk more about the final project in a later lesson, but let me just briefly mention what we're going to do in the project. There's a lot of details for the project are given in the syllabus. The basic idea is that you're going to make a claim about a population, you're going to collect some sample data, and apply an appropriate hypothesis test. So the first step is to think about a topic for your project. What kind of data do you want to collect? What kind of claim do you want to make? And so for an ANOVA test, we can use ANOVA whenever we want to compare more than 2 different populations. And so some examples, maybe you want to claim that 4 different brands of bottled water have the same mean volume. So maybe you want to compare, Dasani to Sam's Choice to Nestle to whatever. And so you go out and maybe you buy some different bottles of each type. You somehow measure the volume in each bottle and do an ANOVA test just like we did. Maybe you want to claim that different colors of M&Ms all have the same mean weight. And so there you'd go out and get a bunch of red M&Ms, a bunch of green M&Ms, and so on and so forth. You'd weigh each one of them on maybe an electronic scale, and then do an ANOVA to test your claim that they all have the same mean weight. So as you go through the homework, and be thinking about what you might want to do your project on. If there's an example or a homework problem that catches your attention, think about how you might try doing something similar for your project. So that's it for the section 12.2 lesson. The homework is posted on MyMathLab.